So, this is computer organization and architecture. This is all up on Angel. This is the crap for this class. Prerequisite is 300, which means that there is programming in here. If you haven't had the prerequisite, I guess I don't necessarily care, but that's kind of on you. So good luck. Let's see. It's,
100 hours spent outside the class.
minimum.
Expectations, okay.
Yeah. Homework, 45% or grade. Quizzes, 15%. There'll be pop quizzes. I'll give them whatever I want. Midterm final, 20% each. If you bomb, the midterm, I will likely give you an opportunity to try to make up some of those points with the final, but not the other way around. So if you get an A on the midterm, then come in and get a 0 on the final, that doesn't exactly tell me that you've mastered the material by the end of the semester. It really tells me that you gave up. 90, 80, 70, normal, grading scale, blah, blah. I guess that's it. Questions? All right, that's the... Huh? No, not even close. Okay, so that's the scoop. So, let's talk about the class. So when you hear computer organization and architecture, what does that mean to you? What do you assume the class is about? This is exhilarating. Any preconceived notions? What's architecture? How something's built, right? What's organization? How it's laid out. So computer organization architecture would be the layout and how it's built of computers, the hardware of computers, right? So what is hardware? You're going to give me a definition for hardware. What might you say? Go ahead.
Things that are solid in the computer, things you can touch.
Things are solid, things that you can touch. Okay. Yeah, I don't disagree with that. Give me some more. There's lots of things that are, for instance, here. Solid. I can touch it. This is the outside case. Is that hardware? Potentially make an argument that the case is hardware. But when we, if we're taking this back to that idea of organization and architecture, chances are this isn't what we're talking about with hardware, right? So what's the next step? Saw a hand at some point. They give up. Who had their hand up? Tim, you had your hand up? Go ahead.
I would say like the physical aspect of the computer.
Okay. Tell me more.
Like the medium of the software.
The medium. I don't know what that means. What do you think that means?
Just like the things standing in between the data being received from the software.
Okay, we might be going down a decent path here. So hardware is physical. You can touch it. It's it's a solid thing, and you think it lays between the software and something else. Software and the user, something like that. Okay. So what would that imply about hardware?
The motor? I would say motor. It runs everything.
Runs everything. Motor. Okay. How does it run things? Give me an example of a piece of computer hardware. Let's go that route. Motherboard. Okay, what is the mother? Yeah, it was the worst example you could have picked. Because you didn't go too far from it. Okay, so what does the motherboard do?
It links together the rest of the hardware.
Links to everything, right? Okay, so let's take a specific part of the motherboard. Let's take the memory slots on the motherboard. Okay, because they're hooked into the motherboard, and you would plug RAM chips into it, right? Okay, well, what's the job of a RAM chip? So if you go out and you get a 4 gigabyte, DDR3 blah 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 gigahertz RAM chip, what's the job of that? Well, first of all, is that a piece of hardware? Yeah, we'd call that hardware. Okay, I agree. So definitely something physical. Definitely something we could touch. Definitely something that goes in the computer. Definitely something that lives between the software and the hardware and the user, right? Okay. What's the job of a memory module?
Just store the information that's in use.
Okay. Store data. How does it accomplish that? Have we ever written a computer program that stores data? Toss it into an array or something like that? Sure. How did you accomplish it? It's not a trick question. When you wrote your last program that used arrays,
By changing things in memory addresses.
okay, you're going even deeper than I expected. So, you wrote some code, some Java code. You compiled it in like Eclipse or something, right?
Right.
And you ran it. And then you interacted with the program through the keyboard and things that were on the screen, and ultimately it saved crap. So what was the problem-solving medium? It was the programming language, correct? What about hardware? Somebody had to create that memory module to store stuff. How did they do that? What's that hardware chip comprised of? Is there lines of programming code in there?
Switches.
Okay, switches. What kind of switches?
Just simple on-off in the chip.
Okay, so there's like chips and crap, right? So really kind of machines. Would you say that a chip, a hardware chip, any kind of generic hardware chip, would you say that's necessarily dissimilar from a method? What's a method in computer programming? Reusable chunk of code that accomplishes a task, right? So when you go out and you get a chip for Bluetooth, isn't that something that is reusable? The manufacturer created 4 billion of these Bluetooth chips. You soldered it onto this board, hooked it up in the right way, whatever that is. And now what does it do? It solves the problem of running a Bluetooth radio. Isn't it the hardware version of a method? So is hardware really that dissimilar from programming? Not really. Maybe it's the difference between, it definitely is the difference between writing a program that uses the general purpose tool computer to run your software versus actually creating the tool. So almost like designing a house and building a house. Two separate things, right? Okay, so hardware, we might say, is a physical piece of equipment comprising let's just say comprising various circuits which likely work together to accomplish a task. Hardware is a physical piece of equipment comprising various circuits which likely work together to accomplish a task. Fair enough? So up to this point, we're programmers. Why do we care about hardware?
Anything that can be done in software can be done in hardware.
Okay.
It's just whether or not
Yeah, I think that's fair. So piggybacking off of that, why would we choose to do some things in software and some things in hardware?
some things you can do faster in the software, and other things you can do faster and easier in hardware.
Okay. So let's take an example, our Hello World program. So if I want to create a solution to the problem of displaying Hello World to a screen, okay? The way I would solve that in a programming language would be write the handful of lines of code that display Hello World to the screen and run it. What would the solution be in hardware? How would you solve the Hello World program, the whole display Hello World problem in hardware, generally speaking? Well, first of all, I got to figure out where am I displaying it? Maybe a little LCD screen or something like that. So I got to go out into Radio Shack and buy a little LCD. Gonna have some wires hooked up to it, right? Whatever they do. All right. And what else do I got to do? Well, it depends. If I'm going to make this not general purpose, like the only thing that this particular piece of hardware does is display Hello World, kind of the I am Groot thing. I knew I was going to work that in somewhere. Okay. Who did not get the reference? You didn't see Guardians of the Galaxy?
Oh, not yet.
I don't think you need to see it in order to get the reference.
Really?
I haven't seen it yet.
I've seen it.
You haven't seen it?
No.
But you still got the reference?
Yeah.
How did you get the reference?
Because it's been all over the
Previews
internet.
and stuff like that? The interwebs?
The
Okay.
interwebs that have it.
Well, so assuming we're not going to be general purpose here, we're going to just say this piece of hardware specifically displays Hello World. In that very specific order. This entire vocabulary is I am Groot, specifically in that order. Okay. But all this hardware is going to do is display Hello World. That's it. So we've gone out, we got our LCD. Now what else are we doing? Well, the LCD is a piece of hardware somebody else built, right? So we're going to kind of forget about that side of the coin just because it works. LCD works, and it's got wires and crap that go into it, and they work somehow. So assuming we know how that works, we just need to send the necessary signals, whatever that means, to the LCD so it specifically displays an H, E, L, L, O, so on and so forth, right? And probably plug a battery into it so something is powering this whole thing, and then say, ha, Hello World. So how long does Hello World take to write in Java? A minute? How long would Hello World take to build in hardware?
How many times do you need to go back to see it?
More than a minute? Okay, probably more than a minute. So in that particular example, writing the program for Hello World might make more sense, right? Well, when would there be an example when creating the hardware Hello World solution might make more sense? One measurement here is time, correct? We already decided that if time is your main measurement, software's winning. Okay? But when might time not be the main measurement? What if you're creating a special purpose kind of tool? Here, we'll do this off like kind of a joke thing. So you've seen these people out there that have the drones, right? That are flying drones over like, mobs and things like that. What if somebody hung a LCD off one of those to deliver messages? Well, that's going to be a better solution for hardware than if you'd like hung that laptop off of there, right? And just hope the screensaver doesn't kick in. Okay, so when you have a specific solution like that, sometimes hardware makes more sense. Can you think of anything else? Any other situation when hardware might make more sense?
For fuel regulation for a car.
Fuel regulation for a car.
Yeah, the amount of fuel pumps has to be.
Yeah, but why can't that be software?
Well, if you do it in the hardware, it's going to be permanent, and then if the computer fries out, it'll still work for most of our race cars around the back home. We do that.
Okay, so you're thinking it's less general purpose, but if you hard code the solution in, there's less moving parts that can go wrong. Therefore, you can kind of rely on it, and probably on beyond that, it's also fast. So we almost take it back to the example we used with Java as to why Java's not always the best solution for all programming problems. Because Java is an interpreted language at the virtual machine level, that adds one extra layer of speed reduction, right? One extra delay. Same thing would be if we have your modern car that has like one central computer, which they're almost kind of going to that now, right? You got this computer that knows a whole bunch of stuff about this car. And if you have everything run through there, and this isn't the Volkswagen that's supposed to get you back and forth from work, but instead it's the race car meant to do things, where fractions of a second make a difference. You might have everything running through this general purpose computer, and there's delays in there, right? Plus, if the computer goes bad, all the stuff that's run by the computer also go bad. As opposed to if you have each individual part of the car running off its own little hardware solution, only the part that went bad, only that aspect of the car is broken. Make sense? So, punchline here is we can certainly see examples where hardware might make more sense than software, and vice versa. Okay? So, back to the why should programmers care about hardware? Maybe I'll pose this question. Is programming and hardware architecture two distinct things? Are they actually very closely related? What is computer programming? If you had to concisely define computer programming, what would you say?
Giving the computer instructions to do something.
Okay, solving a problem using a computer. Okay, so solving some problem using a programming language which instructs the computer, giving it instructions. What would you, if you're building that hardware, we used the example a few minutes ago about the hello world thing, aren't you going to go out and get the tools you need to do it, just like getting the programming language? You're going to wire them up, you're going to write the syntax, you're going to solder the thing together the right way, put the battery in, hit play. Now it works. Is that necessarily that dissimilar from each other? One's a little bit more physical than the other, but you're really doing problem solving, right? So, should computer programmers care about hardware? Is the answer yes or no? Of course?
Yeah.
Why would you say of course?
Well, because, like you were talking earlier, you can do it. Some things are going to be easier and faster in hardware. Some things are going to be better to do in software. So if you're programming something and and it's going to be non-general purpose, then you can do it in hardware and make it faster and more reliable. Might as well do it in hardware.
Okay. My experience amongst computer scientists has typically been you rarely have, not that it doesn't, not in today's world, not that this person doesn't exist, but you rarely have the hardware guy. Back in the early days of computing, let's say, you had hardware guys. For instance, Wozniak from Apple. He was the hardware guy. Steve Jobs was the, kind of the, I don't want to say brains, he was the business guy. Wozniak was the technology guy, but he was all about hardware. He built the first Apple computer. He didn't go on to Newegg and start ordering parts. He built it, just soldered it all together and said, go. But today you don't really have people like that because we've abstracted so far from that at that point where we don't really think about the individual pieces of hardware anymore. The hobbyists today, what do? They build their own gaming rigs and stuff like that. So they pick out their case, they pick out their liquid cooling, whatever. They grab a fast, high-performance hard drive, processor, memory cards, all that crap. And it all comes in one package. You stick the motherboard in, the processor falls into the little thing, you hook the little thing down, you put the heatsink on, done with that. Brain's installed. Memory takes all of 10 seconds to pop in, hook the hard drive in, now you got a computer, right? That's what cool kids do now. That's the hardware guy. He ordered 9 things off of Newegg and now put things together. At no point, how many of you have built your own computers? In part of that process, did you ever pull out a soldering iron? But I regretted it immediately. Ever twisted any wires together to make a connection? That's not the world we live in today. We've abstracted so far past that we don't think in that world anymore, right? So my experience has been amongst computer scientists today, you have some people who are programming specialists. That's what they do. They write software. Then you have the folks who are programming specialists, hardware hobbyists. And there's been some products, and we'll mess around with a couple of them here in class actually at some point, that have come out. One's called Raspberry Pi, if you've heard of that. It's kind of a computer on a chip. Another one's called Arduino. Arduino is a programmable circuit board, so you can actually write software for hardware. Kind of almost the hybrid between those two, but you can create little interesting projects like that. So for instance, with Arduino, you can go out and get an LCD screen, plug it into the Arduino, write some software that runs on the Arduino that says, send these electrical signals to the LCD screen, and now it does its thing. So should programmers care about hardware? Of course. But not all of them will do anything about it. And that's okay. There are there's much division in the industry today between going out and getting a job as a computer engineer where you're actually building hardware and getting a job as a software engineer where you're writing software. Very rarely you're going to be in a position where, you're going to be writing business software during the day, and then your boss says, okay, we need you to go downstairs with the soldering iron, and, the Dell server is having problems. No, what do? You call the Dell tech guys, and they come in and replace the hard drive and just say, we're done. Okay, so, that's the world we live in today. Okay, so now let's start talking about some of the crap that goes into hardware. So kind of step away from the idea of computing for a second. So let's just talk about analog signals. What do you know about analog signals before you read the slide and stuff? Most of us have at least probably heard the word before, right? Analog. What can you tell me about it?
It's different than digital.
It's the other guy. Okay, so, our world, the real world, is analog. Computer world is digital. That's the difference from, okay. So, as I say here, analog is a bunch of floating point values, but with arbitrary precision, infinite precision. Just keeps going. What's the side effect of that? Like, for instance, let's say I'm taking a temperature reading outside, but I'm taking an analog temperature reading. So let's say right now, what is it, maybe 71 degrees outside or something like that. Okay, but it's probably 71 point blah, 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 blah. Just keep going with decimal places, right? We're going to check it again in 5 minutes. What are the chances of it being the exact same temperature in 5 minutes? Not as good as we maybe think it should be, right? Because of the infinite precision. Depending on how many decimal places we go out to, it could be a zillionth of that's actually not a word. It could be a quadrillionth of a degree cooler in 5 minutes, right? We usually don't measure temperature that way, right? We think about it as being either 71 degrees or 72 degrees. The news station doesn't say it's going to be 71.25 out today. They should start doing that. I wonder if anybody would actually notice. See how much people pay attention. Okay, so analog signals are floating point values with infinite precision. The example I like to use is the rabbit ear TVs. Any of you ever watched, had TV where you used an antenna to get the TV? Tell me some properties of that. So you use the antenna, you're messing with it so you get a good picture, right? Well, what happens when you don't have a perfect picture?
You get your buddy to stand.
Do you still have a picture? You got something. Okay. So with analog TV, there's all sorts of ranges of TV signal, right? You know, you might have a lot of snow on the screen, but you might still be able to make out the picture. You know, it might be a little fuzzy, or you know, it just has the weird waves sometimes, things like that. But still, you can tell, you can watch the show. You know, then you finally kind of get it tuned just right with the right amount of foil and the right person hanging on, like, okay, we got it right like this, you know, blah blah blah. You know, but there's all sorts of places in between. It's not either we have perfect TV or we have no TV. Analog, it's everything in the middle, right? Now with digital, this is our computer world. Okay, these are values, could be floating point values, might not be, that could be integer values, but the punchline is they have fixed precision. So this would be like saying it's 71 degrees right now, and it is 71 degrees in 5 minutes. And the way we're measuring it is we are, you know, maybe we decide we're taking it out to 2 decimal places. So maybe it's 71.13 degrees now, and in 5 minutes it's still 71.13 degrees. What comes after those 2 decimal places could be completely different, but we're going to call those equivalent temperatures. That makes sense? So fixed precision is an important aspect of digital. And I use the example of digital TV like DirecTV. Any of you have DirecTV or Dish Network at home? Nobody? Even digital cable is fine. Time Warner or any of those? Okay, somebody has something of that. I like to use the Dish technologies because this happens most often with them. So let's say you have DirecTV. You're watching a show, everything looks good. It's high definition. All of a sudden a rainstorm comes in. What happens? No TV. Doesn't it get a little fuzzy?
No, you just get a blue box that says searching for certain.
Yeah, your TV either looks great or it's not TV. That's digital. There's no middle ground when it's trying to put together that picture. You know, if there is a middle ground as it's going out, sometimes you'll see the screen get very pixelated. You know, see the boxes kind of show up because the packets, how they're coming into the TV screen for high definition TV, they actually, I think the screen is split up into a whole bunch of, you know, square pixel blocks. So you might actually start losing some blocks first, and then it just cuts out. Once it loses a certain threshold of accuracy, it says you no longer have a TV signal. So digital would be something like that. Now, the world is analog. Computers are digital. Now, we use computers a lot, right? We use the world a lot. So we need to somehow marry those two together, don't we? So if we have a computer, like for instance, any of you can go on to a website right now and check the weather outside, correct? And get the current temperature read from some, you know, tower at the airport or something like that, in Milwaukee Airport. So they have some machine out there that's reading temperature constantly. It's feeding into some sort of computer. The computer's taking that temperature, probably uploading it someplace, blah, blah, blah. Well, we're taking analog data. That's the sensor up here. We're cleaning it up. So maybe we decide, okay, well, that analog data is taking our temperature to, you know, 90 decimal places. Let's go ahead and get it down to 2. So you kind of see here this weak, noisy analog signal. So maybe you, let's just use an example that this is a temperature reading. Let's just say this is between, you know, here and here is 1/10 of a degree. Something like that. That makes it more accurate in this case. Okay, and this is over a 5-second period of constant reading. So we see how it's kind of all jagged all over the place, blah, blah, blah. So one thing we can do is we can clean it up by either truncating or rounding or doing something to the signal to give us a smoother curve. Make sense? So there's less data points here than there are here. Because what we've done here is we've cleaned this up and said the only data points we really care about are maybe here, 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 here. Where here it's like here, 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 blah, 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 all over the place. Okay? Now finally, before we get it into our computer, we have to convert that analog to a digital signal. And the analog to the digital signal is kind of what we're going to be talking about a lot over the next couple of classes. Okay, that's where this converter comes in. Now, what does this look like to you over here? If analog looks like this, and they're representing digital as a whole bunch of individual wires coming out of here, what conclusions might you draw about digital? How does this machine work? We use this example about weather, taking the temperature, and we decide the current temperature outside is 71.25 degrees. That's what the average of this guy has come out with. So for this particular second that we're sending this to the analog to digital converter, we're sending the temperature 71.25 in here. Okay? What is it doing to that 71.25? It's converting it into digital data. What's the digital version of 71.25? If we go back here, we say a digital signal is values with fixed precision. That's a digital signal. What's digital data? It's looking a little different over here. So think about that for a minute. So how do we represent our digital signals? So a human being can remember values like 4.5 and understand that that represents a value. So for instance, with our 71.25 degrees outside, that means something to us, correct? Okay, that has some meaning. Computer doesn't know that has meaning. Computer is going to take that as input, and then we're going to have a program that's going to decide, okay, well, if it's greater than 63 degrees, we're going to say it's warm, or something like that. We can build the thresholds in. So digital systems represent values using tiny switches called transistors. Transistors can remember two values. Well, they can remember one of two values, either on or off. All right. What did we do before transistors? Vacuum tubes. So if you remember from your 150 class, you probably saw some of the older computers, EDVAC and UNIVAC and stuff like that, these giant computers the size of gymnasiums. And you had people running around screwing light bulbs in, right? You want the transistor to be on? On. You want the transistor to be off? Off. That's how we faked transistors before they existed using vacuum tubes. Well, transistors can hold that value within themselves. We don't have to turn these vacuum tubes on and off. What else did transistors allow us to do? What was the biggest benefit of transistors?
Make things smaller.
A lot smaller, right? I mean, the number of transistors that are in our cell phones today are far, 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 far greater than the number of vacuum tubes that were in the largest computer 50 years ago. I mean, not even close. Okay, so transistors are ways of remembering single values, on or off. So digital data. So we take a digital signal, and how do we represent it using digital data? And digital data is often represented in a binary system. What's binary? I see Thor giving me a binary signal. Okay, so well, you say machine language. Okay, machine language would be an example of a binary system, zeros and ones, right? But binary system is any system that has two values, one or the other, one or the other. So a single transistor can represent on-off. Could easily mean 1, 0, yes, no, true, false, up, down, high, low, whatever. So all problem solving done in the digital world is done by taking, well, reading data and making decisions based on whether the data is on or off, true or false, yes or no, up or down, 0 or 1, blah, blah, blah. Okay? And we do this enough times and in a complicated enough way and in an interesting enough way, we actually solve real problems. So, more complex systems means more transistors. So let's take a simple system. Light switch. So you have electricity flowing to a room in your house, a light bulb in the house. Now, without any sort of switch, that light bulb's just on, correct? There's power flowing to this light bulb. The light bulb, when electricity comes to it, it ignites the filament and, you know, all this the light bulb stuff happens, right? Okay, that's a whole other problem. Somebody else solved. They solved the, you know, contain fiery light without burning house down. Okay, that was last week's lecture. So if we just have electricity flowing to that, lights on. But we don't keep the lights on in our house 24/7, right? We like to be able to turn the lights off for multiple reasons. We like to be able to sleep. We like to save a little electricity. We don't want to have to be replacing light bulbs every 3 days. All sorts of stuff like that. Okay, so we install a switch. So we can think of a switch as a single transistor. When the switch is in the on position, we expect the light to be on. When the switch is in the off position, we expect the light to be off. The digital representation of that might look like this. When we hit the off switch, we have the logical value 0. Or back to the previous slide, we might say this is a low signal. Or this is down. Okay? As soon as so the vertical thing here is on or off. Notice that's the only positions is in. We don't have the nice curves here. We have on, off. Off, on. Make sense? Now, what is this axis? The length here. What's this guy right here? What's that a measurement of? Time. How long was the light off? Correct? How long was the light on? How long was the light off? So these switches block the electrical signal to the light. So we can think of that as transistor logic for a very simple exercise. Okay? Now, these are more a light switch. The way it works, it has to have some other stuff built into it to make sure that, you know, it doesn't melt and stuff like that, because you have electricity flowing into it, and that's scarier than some other things. But you know, the point is, it's at least a good example of what we're talking about here. Now, sometimes you have switches working in conjunction. So you might have 3 different lights in a room, and each of those lights might work a different way. And you might have a dimmer switch. How do dimmer switches work? Okay, so dimmer switch, you can turn it all the way down, you can turn it all the way up, all the way up, all the way on, means the light's going to be bright. All the way down means the light's going to be off. But in the middle, you can have different amounts of light. How does that work? Is that still digital? Or is that analog? Go ahead. Okay. What do you think? Why do you think it's analog? Okay. Anybody think that it's digital?
I think it could be digital.
Okay.
It'd be easier to make it analog.
Well, how would you do that digitally?
You would have to have a ton of different settings for on and off, and when one of them is on, it would be a certain light setting. And you would just have to go from high to low.
Okay. So to kind of subdivide those things up, so something that Thor said back there is that there's a resistance, right? So when you have these dimmer switches, so the way dimmer switches work is analog. So you have you have a resistor in there, and electricity is always flowing through. The dimmer determines how much electricity gets to flow through. And then a different amount of electricity is arriving at the light bulb, which means it's brighter or dimmer. Okay? So what if we subdivided that problem? You're like you said, this is not convenient, but we could pull it off. At least, could we actually pull it off identically? We could simulate it pretty well, or emulate it. We could emulate it pretty well. We could break it down into, maybe we decide that a dimmer switch has, we'll just make it an easy number, 10 different light settings. You have off, you have pretty dim, you have less dim, you have even less dim, so on and so forth, right? So we break it down to 10 different settings. And for each of those settings, we have the correct transistor-like setup such that the correct amount of electricity gets through. But we're not always allowing a stream of electricity to get through. We're just basically forcing everything to be, this is what gets through. This is a fixed amount. It's always this for this light setting. It's always this for this light setting. So we're solving the same problem 10 times. But we're really not actually solving the dimmer switch problem, because the dimmer switch probably has 50 different brightnesses in between for a standard dimmer. You know, there's probably a bunch of different shades you can get in there. But we can certainly emulate it. So a dimmer switch would be analog. Can you give me a similar example with light switches that would be digital? How many of you have had one of those lamps that has a three-way bulb? So turn it once, it's one brightness. Turn it a second time, it's another brightness. Turn it a third time, it's another brightness. How is that digital?
So there's three constant light differences, and they're always going to be those same levels of light. They're not going to mix, like, or kind of rotate or shade into a brighter light.
Okay. We could actually solve that problem two ways, though, can't we? And the way it's solved is not at the switch, typically in real life. There's a three-way bulb. So actually, the solution to the different brightnesses is built into the bulb, not the switch. The switch says we're going to allow full electricity to come through on this first switch. So low, medium, high. Three distinct settings that would have outputs, single outputs, either this setting is full on or this setting is full off. This setting is full on or this setting is full off, like that. And the light bulb knows how to interpret, you know, the settings coming, the electricity coming into it as to which setting we're on. Okay, so now you have two products working hand in hand. Okay, so now types of digital signals. So we have something called edges. So these are long-term changes in a value. So a 0 to a 1 is a rising edge, a 1 to a 0 is a falling edge. So this would be something that's going on for a very long period of time, like our light switch. You turn the switch off, and it's off for 7 hours. That's an edge. We would see, just like we saw it here, this type of thing, but long duration ones. We call that an edge. Now, pulses work a little different. Pulses are short-term changes in value. For instance, a reset button. So you have positive going pulses and you have negative going pulses. All right, we have different pulse waveforms. So now we're starting to limp towards technology. Ultimately, where we're going with this is frequency. Okay, what is frequency?
How often something happens?
Okay. when we think about what are some things that have frequencies? So like Wi-Fi, right? Wi-Fi has frequencies. What are the common frequencies that you're used to dealing with in Wi-Fi? The 802.11b G standard is across a certain frequency, and that frequency is divided into 11 channels, right? And what is that frequency? 2.4 gigahertz, right? Okay, so you have the 2.4 gigahertz channel, and then little jumps between 2.4 gigahertz and I think it's 2.62 gigahertz or something like that. Is that where those 11 channels are divided up? Okay, so now we're talking about like almost an interstate that data is flowing across. Now, if we have two Wi-Fi things in the same room and they're both operating on channel 0, so let's say they're both operating at exactly 2.4 gigahertz, what's the downside to that? What can happen?
They can shadow each other and cancel each other out.
Okay, create collisions. And you have, my laptop maybe is on one network, another laptop's on another network, and we're reading each other's data and not being able to interpret it because it's not what we expected. Stuff like that, right? Now, it actually becomes interesting. We think of these as just radio signals, and so often it's easy to just say, well, radio is this old-timey technology, right? You just hear the word radio and you feel it's old. The reality is like every single day we have, somebody's buying the next wavelength of stuff in space. The amount of crap, the amount of radio waves that are hitting our systems right now, like this very second in this room, is ridiculous. We have the cell phone wavelengths, we have Wi-Fi wavelengths, we're going to have wavelengths related to electricity in the room. What else? Each of our laptops are going to be giving off Bluetooth radio. Each of them have Bluetooth radios on them. So they're going to be bumping into each other. So we have all this crap. And what do these create? These create like little streets, little interstates in the air that we can't see. And that's a frequency. So frequency, you mentioned, is how often something happens, right? So if something happens, let's say 2.5, we have the 2.5 gigahertz range. And something happens in that 2.5 gigahertz frequency. Is that going to happen? How do I ask the question? Let's take it down to a simpler example. Let's just take it down to the basic of hertz. So if something happens every 1 hertz, that's going to happen more often than something that happens every 3 hertz. A 3 hertz thing, right? Okay. Now, can both of those things coexist? Or do they have their own conflicts? Are there deeper conflicts there? Let's say that Amish is going to yell Groot every 3 seconds. Okay? And Tim is going to sneeze every 60 seconds. Will there be a point in time that you yell Groot at the same time as he's sneezing? Is that problematic? Are our ears listening to those frequencies? So you guys are both kind of sharing the same channel, the frequency channel that is noise that the human ear can pick up, right? Okay, and you are jumping on that frequency at different points in time, but sometimes you overlap. And when you're saying Groot at the same time as you're sneezing, might we misinterpret your Groot during that period of time? You might not hear it right or something like that, or somebody in the back might miss it and say, "Oh, you missed your, missed your opportunity," or something like that. So those are conflicts. When we're dealing with a bunch of frequencies, how do we deal with that conflict? How would we solve that problem? So kind of put the technology on the side for a second, and now we're just dealing with the problem of every minute Tim's going to sneeze. Every 3 seconds, you're yelling Groot. But now we need to make sure that we don't miss Tim's sneeze. We also don't want to miss your Groot. What are some ways we solve that problem?
Prime numbers.
Huh?
Prime
It's
numbers.
prime. It's got to be prime numbers, right?
It's not wrong.
Okay, so tell me.
You alternate prime numbers. So if Tim's 3, if he does it every 5 minutes, then they'll never catch up.
Okay. I got you. So you're like kind of 2 steps ahead. Okay, I'm with you. So I'm saying, how do we solve this problem if we're sticking to our he's every 3 seconds, he's every 60 seconds. So what Dave is suggesting is, hey, if we make it so that your guys' time increments are staggered using prime numbers, such that there is no, like, if you are doing it every, actually, they'd both have to be prime numbers, right? Yeah, so if you're doing it every 2 seconds and you're doing it every 3 seconds, you guys would never overlap if you started at the same time, correct? So that would be a solution,
Yeah,
but
you overlap at 6.
not if you both start at the same time.
I'm sure there's overlap though.
Both start at time 0. After 2 seconds, you fire. 1 second later, you fire. 1 second later, you fire. 2 seconds later, that's where you would overlap 2 seconds later. Okay, so even prime numbers aren't a good solution.
3 and 5.
So it's got to be
2's not a prime number.
farther apart.
2 is, yeah, it had to be 3. It had to start at 3. So 3, 5, 7, 11.
Okay, well, fair enough. But before we go down too far down that path, I want to deal with the problem, an earlier day problem. That is the problem where Amish is doing something every 3 seconds, and Tim is doing something every 60 seconds. Clearly, there will be overlaps. Now, the problem we're trying to solve is we don't, as listeners, as human beings listening to this, we don't want to miss your message, so we're going to assume your message is important, and we don't want to miss his message, because we're assuming his message is important. But we know for a fact that there will be times where you both are delivering your message at the same time. How would we solve for that problem? Just don't think about technology. Just put yourself in the shoes of, okay, we need to make sure we don't conflict with each other. How do we solve that? This is related to this non-periodic versus periodic pulse trains. Periodic would be what we're describing here. Every 3 seconds you're doing something. Non-periodic might be 3 seconds, 2 seconds, 18 seconds. It's not predictable. Do human beings need periodic pulses for us to hear? We could be sitting here in complete silence, expecting nothing. And all of a sudden Tim can just let out a monster sneeze, and we'd hear it, right? Why? We didn't know it was coming. Are we constantly sampling the sound waves? And there's probably a frequency to that too. How often our eardrum and brain can process sound signals, but it's happening extremely often, seemingly, right? Okay, so we're constantly sampling it. Isn't that analog? That's an analog issue, right? I'm constantly sampling the sound, so I don't need to know when he's going to say it. But now, what if we're in the digital world? So we're gonna restructure our ears a little bit. We're gonna decide we only listen every 1 second. So every 1 second, we will sample the current sound in the air, that we don't miss anything. And we just happen to make sure we schedule everybody who's going to do things that they're at least a multiple of a second, not every 1.27 seconds Tim sneezes. That would be funny. How long until that gets annoying? He would probably pass out after about 3 or 4 sneezes because he couldn't catch his breath. So we're going to sample the air every 1 second. And you're going to do something every 3 seconds, so we pick it up, right? And he's going to do something every 60 seconds, so we would pick it up. But now when we hit second 60, you're going to be doing your thing and he's going to be doing his thing. So we're all going to hear both of those things at the same time. Correct? How do we separate those two? What strategies could we employ to fix this problem?
Put us in separate rooms.
Just put it in separate rooms with an observer. The observer gives the thumbs up. Now, if both of you had the same voice, well, here we got to try this real quick. So you got to say Groot, and you have to fake a sneeze, and we need to be able to tell how much conflict there is. Are you prepared? Are you prepared?
Sure.
Okay, so on the count of 3. Okay, 1, 2, 3.
Groot.
Yeah, good enough. All right, so there was certainly some conflict there, right? All right, because your guys' voices aren't so dissimilar. Could we say that Amish is going to go onto a higher pitch, and you're going to go a lower pitch? Will we be able to hear it better? By separating, we're not as close on the frequency scales. We're kind of mixing terms a little bit there, but let's just say it's correct for right now. So that could be one thing we're going to do. Now that only solves the problem maybe a little bit between two people. We have one really high pitch thing and we have one really low pitch thing, and maybe we have a good chance of hearing both of them. And then you have the people who's, it's outside of your hearing range. Isn't there something like kids can hear higher pitch sounds than adults? So, those variables get thrown in here a little bit. But generally speaking, by even taking that little movement, that little thing, we could probably separate out those two sounds enough where we can tell which one was which. Right? Well, what if we put a third person into this equation? And a fourth person, and a fifth person. Now we have all these different sounds that are happening. We're sampling the air for sound every 1 second. Okay, so we're almost trying to stumble upon the solution that they digitally came up with. Because we really are mimicking that. If we think about our computers that are putting out these Wi-Fi signals, they're pulsing every so often. There's a period of time when they sample the wavelengths, sample their specific frequency to see if there's new data up there. Something we'll talk about some in here, but like we take, so let's take a wireless connection like 802.11g, which is on a 2.4 gigahertz spectrum. That's the radio signal. That's the medium. That's the highway that data is flowing across. How the data flows is defined by something else. It's defined by the TCP/IP protocol. Okay, that describes how the data flows. So the data is flowing, and these individual machines, and it's a wireless Ethernet, is how which is a bus-based technology. I won't go that far with it because that's more of a networking concept. But the point is that each of our computers, when they are looking to see if any packets have come back from me, when you type in google.com on your computer and you press enter, it sends a request out, and now it's waiting for a response. Well, this computer is going to constantly sample the wireless network, waiting for the response that was meant for him. And he's kind of like fishing through the water up there, and as soon as this is mine, pulls it in. Okay? So every single packet is flowing against this network interface card here that happens to be a wireless card, and each computer only takes the stuff that belongs to them. So every so often, all of our computers are going up and we're checking the wireless space on a specific channel or across a couple of channels. When we join a network, we join networks within a specific channel. We're not always on the same channel, so the newer the network, typically the more simultaneous users they can support, and they sometimes support them over multiple channels. So that's kind of how they spread things apart. But in any case, when we start sampling so often and pulling things in, we introduce a lot of noise. Correct? You know, what keeps that data from getting corrupt? So if we are all, you know, let's say 7 or 8 of you are all doing your, you know, your sneezing, your groots, your screaming, whatever it is that you're going to do, that's adding a whole lot of data in the air. Now, even if all that data is happening at the same time, which is how a wireless signal would work, right? I mean, you know, if all of us do a Google search right now, we'd expect to get our results. You know, not for half the class. Huh?
Not on this internet.
Really? Is it bad today?
I don't know.
I've been streaming Game of Thrones all day. I didn't have any problems. It's like no issue.
Well, that's why you're on Wrestle.
That's right. Okay, so that's going to cause conflict. How do we fix that? When you have everything all demanding to use the same interstate at the same time, and we need to make sure everything arrives at their endpoints, and we need to make sure that the endpoints are able to read from that data. There's a lot of problems that need to be solved at the same time there, right? So right off the bat, what did we do? We said, okay, well, maybe Amish and Tim use different pitches. Maybe that gives us a little bit of a better chance of hearing them clearly. Dave suggested, you know, if we schedule them such that there isn't overlap. Seemingly a good idea, right? It certainly works at airports. We don't want planes taking off and landing on the same runway at the same time. It's kind of get messy. Okay, so certainly that kind of solution seems to be a smart solution. Whether it's prime numbers or whatever, we're going to schedule such that there are not collisions, that you would not group at the same time as he sneezes. Now, what if we avoid the idea of a prime number and we just decide, okay, well, at second 60, when you guys would have your conflict, one of you is going to wait a second. How would you decide that as human beings? A little bit ago, somebody said something about interrupts. Maybe somebody gets interrupted by the other one. Somebody else suggested something about putting them in different rooms. Now, again, the slide I have up here is non-periodic versus periodic pulses. Non-periodics don't have a pattern. Periodics do have a pattern. Patterns are important for digital logic. If something's going to happen every 3 seconds, it needs to happen every 3 seconds. If something's going to happen every 60 seconds, it needs to happen every 60 seconds. How can we allow you to do your thing every 3 seconds, you to do your thing every 60 seconds, and not break that stride, yet still not have a conflict? Both of you are operating in the hearable space, listenable space, whatever. Whatever's the correct, probably neither of those are correct, but whatever. The problem we're trying to solve is to make sure everybody in this room hears you clearly and also hears you clearly. But we're saying that you have to do it every 3 seconds, you have to do it every 60 seconds. You're both are starting at time 0. So there's a guaranteed collision at time 60. Correct? How do we make sure that only one of you is heard at time 60, but that both of you ultimately get heard? And that both of you remain periodic. Go ahead.
You have to have like multiple sound waves.
Well, that gets back to the hearable space. We're all operating on the exact same sound wave. There's only one wave that we all hear on, even though that's not really true. Let's just pretend that's true. So you guys are, when you speak and he speaks, they are colliding with each other. So both of you have to do it at the right time, yet we should only hear one at a time. How do you solve that?
Just have selective hearing.
It's like that's where we put them into the different rooms. We happen to both have, every one of us has 2 ears. So we pipe one ear into one room, and we pipe the other ear into the other room. And
Are we implying that we hear them both at the same time?
I'm not implying that. I'm just implying that we have to both, all of us as observers, listeners, have to hear them individually, but they each have to do it on their schedule. Can't break stride. Got to be periodic.
Record and separate it later.
Okay. So we could have some sort of intermediary, somebody in the middle, who kind of orchestrates, plans the whole thing, right? So as you make your noise and he makes his noise, and that person detects that, oh, both of these happened at once, and I was expecting this data. They capture both data, but they deliver it to the listeners independently. So maybe they stagger it by a second, right? But both of you guys maintained your necessity to do it at a single period of time, right? Without breaking stride. But we delivered it to the listeners, potentially out of sequence, so that we wouldn't have conflicts. Okay, so we might have an intermediary in there. Things that go into a frequency are period, how often something's happening, as well as the width, how long does it happen. So we take each of those noises, the groot and the sneeze, depending on how violent the sneeze is. Those might be very, they might be differing length. So your groot probably takes 1 second. His sneeze might take 3 seconds. Correct? So now we throw that little curveball in there. Does he sneeze every 60 seconds? Assuming a sneeze takes 1 second, or does he sneeze every 60 seconds, assuming a sneeze takes 3 seconds? Even if a sneeze takes 3 seconds, what does 60 seconds mean? Is it time zero progressing 1 second at a time? Or as soon as he finishes one sneeze, does the timer start again? So he's actually offset by 3 seconds. See what I'm saying? These are ambiguities we'd have to deal with. So width does play into it. How long does something occur? Or at least could play into it. Thinking about it from the perspective when we start moving back into digital, when we sample something, we need to make sure we sample it long enough for the width. Our hearing happens to be pretty good at just kind of sampling whenever we need to sample. But if our hearing could only do something for 2 seconds long, let's say we can only hear something for 2 seconds, then we had to, repower or something. And his sneeze was 3 seconds, we're going to miss the final second of his sneeze. So we couldn't sample the air long enough. Okay? So both of these things kind of play in. Now, frequency. What do you know about frequency? Frequency is typically measured, I referred to it earlier, in something called hertz.
Cycles per second.
It is cycles per second if we're talking about CPUs. Yeah, but it's you're not incorrect. Just the word cycles can be ambiguous. We certainly measure CPUs in hertz, the frequency at which things happen on a CPU. So a cycle is, we're going to say a cycle is, if we say a cycle is every 1 second, and you have a 10 hertz processor, that means that 10 things happen every 1 second. Something along those lines. So hertz would be our measurement. Typically we think about things in megahertz and gigahertz and stuff like that because, well, all those other things are already taken up and we have a lot more data we need to pass through now. To calculate frequency, we take 1 and we divide it by the period. Notice that frequency does not take into account width. So for example, we're going to have, and this is period in seconds. So frequency is a measurement, frequency is determined by time in seconds. This is kind of the name of the game for it. So if we take, let's Amish here, who's doing something every 3 seconds, that's 33.33 hertz. What's hertz? Just HD. We never use it, so none of them looked right. I know mega, yeah, I guess. Okay. So that means you're operating at 33.33 hertz. And he's operating at 0.016 or 0.1017. And actually, we got to do this differently. This is actually 0.33 hertz. And this is 0.017 hertz. So that tells us your guy's frequency. You're 0.33 hertz and you are 0.17 hertz. How can we take frequency and figure out how often you guys are doing your thing? Well, 0.33 is equal to 1 divided by period. Well, how do we find? It's just algebra, right? So how do we do the math? Okay, well, period is what we're trying to solve for. So we have 0.33 period equals 1.
1 divided by 0.33 period.
1 divided by 0.33. There's our 3.03 seconds or something like that. You know, because it was repeating the 3, blah, blah, blah. All right, so we can go back and forth between frequency and time in seconds. So that means that something that is, how many gigahertz do we say that Wi-Fi was? 2.4 gigahertz? Okay, so how often in seconds is that signal being transmitted?
Sure what you said.
Okay, so next class, we're going to have a quiz. The quiz will be, what is the frequency, or what is the period of 2.4 gigahertz frequency? All right, so you can go Google it if you want, or you can just do the simple math. But remember, we're dealing with gigahertz, not just hertz. Okay, so you have hertz, you have kilohertz, you have megahertz, then you have gigahertz. Make sense? All right, I'll see everybody on Thursday.